important discussion centers around whether quantum mechanics is complete. When we measure a quantum mechanical system, there is, at least in practice, some randomness in the result. If, for example, we tried to measure the position of an electron in an atom, we would keep getting different results when we tried to repeat the experiment. Or if we measured how long it took a radioactive nucleus, like the one in our Schrödinger's cat box, how long it took that to decay, we would get different numbers each time. Quantum mechanics would correctly predict the average position we would measure for the electron and the average decay time of the nucleus, but it would not tell us a specific position or time yielded by any particular measurement. We are, of course, quite used to randomness in our ordinary classical world. We might play the lottery, and perhaps the lottery is decided by which numbered ball appears at the output of some machine. Often these machines are constructed with various different balls all bouncing around inside the machine, maybe driven by some air blower. And that process is sufficiently complicated that in practice none of us can predict which ball will emerge, and all of us with our different tickets for the lottery will have equal chance. But we do tend to believe classically that if we knew the initial positions and velocities of all the air molecules and balls in the machine, we could in principle, even if not in practice, predict which ball would emerge. Those variables are in practice hidden from us, the precise positions of every molecule and atom and the velocities of them. But in a classical view of the world, we believe they exist. So behind the apparent randomness of quantum mechanics then, are there similarly some hidden variables? Could we actually predict outcomes precisely if we knew what those hidden variables were? Is the apparent randomness of quantum mechanics just because of our lack of understanding of some deeper theory and its starting conditions, some complete theory that would supersede the quantum mechanics that we currently know? Einstein believed that indeed quantum mechanics was not complete, and that there had to be some hidden variables that once we understood what they are in this deeper theory would resolve quantum mechanics and remove its apparent randomness. Relatively recent work centered around a set of relations called Bell's inequalities shows, rather surprisingly, that there are no such hidden variables, or at least not what we call local ones that propagate along with the particles. And that despite its apparent absurdities, quantum mechanics may well be a complete theory in this sense. It also appears, even more strangely, that quantum mechanics is non-local. Now, what do I mean by that? Two particles can be what's called entangled, which is actually a concept made up by Schrödinger in discussing all of this. They can be entangled quantum mechanically to such a degree that measuring one of them can apparently instantaneously change the state of the other, no matter how far away it is. Now, whether you regard this as a cause and effect is actually not at all clear, but still is an aspect about this that seems to happen as if there were cause and effect. It is certainly the case that it's not possible to use this phenomenon to communicate information faster than the velocity of light. This non-locality is very odd, and it's often known through the original, what is called the EPR thought experiment, or paradox, that was proposed by Einstein and his colleagues Podolsky and Rosen. And incidentally, it was apparently discussion of this paper between Einstein and Schrödinger that led to Schrödinger's discussion of his cat, and as I said, also his introduction of the concept of these entangled states. So this is a very strange idea, one that we are, as scientists, still grappling with, this idea of non-locality, but it seems that maybe quantum mechanics is complete as we've stated it, and maybe there are none of these hidden variables, which leaves us with some very bizarre conclusions.